Hi everyone, welcome to the last presentation of Lasagna project. Today we're gonna through all the aspects that compose um, our project, starting from the concept. In particular, Lasagna idea was created from the need of tracking containers and optimize their transit in a port, taking account the existing solutions. And in particular, our solution will provide data in order to perform analysis and use such data exploiting localization algorithms. And all of this stuff will be possible with small beacon on every container and a receiver that will cover specific area. Talking about architecture, we can see how our project is composed of two main parts. The first one is the beacon, which is a L475E discovery board with an integrated BLE module. And on the other hand, we have L072 LoRaWAN board as receiver with a BL shield and an external GPS module. Talking about the receiver, we can see how we implemented or we connected the communication with our GPS, in particular using the second UART interface, but we have the following problem. That is, the RX pin was in conflict with the EEPROM chip select, so we could not use it. And it was not such bad news, but at least we had our TX pin in order to listen the data that GPS want to communicate to the board. And here we have the real implementation of such behavior. We can see how we initialized our GPS and how we manage the stream using a read, in particular a UART read that we wrote, and parsing all the NMIA standard sentences. And in particular, to inhibit our RX pin, we use a GPIO init function. From an higher level, we can see the structure, the pattern we use, which is multi-thread design pattern, and we can see how every component has its own thread, and in particular, the BLE thread has a queue, which exposed to the main thread, which is LoRa, the LoRa thread. Instead, the GPS thread expose an object state in order to aggregate data, and so that the LoRa thread can send all our receiver stuff to the Amazon AWS server. Speaking about software, you can find here our pull request to both Riot, but also in order to implement the SPI buses and fixing some little bugs on C++, but most importantly, our port of BLE module on Riot OS coming from Arduino. Finally, we have a look about the network structures. Nothing is changed, so we have our beautiful beacons that will ping every second, And our receiver will capture such pings, aggregates data, and then using MQTT protocol send such data to Amazon AWS.
So let's talk about the evaluation of our project. These are the graphs from the previous presentation where we extrapolated a candidate for the required lifetime. In this case, these are some dwell times measured in Europe, and these are some of the measured dwell times in Africa. Given these results, which are linked on the GitHub repository, our target is 20 to 30 days. This means that our beacon would be able to sustain the transit in basically any port worldwide, which is a good target. And so that's our goal. We start by considering the batteries, which are, at least in this approximation, 3 AA batteries, so about 7.5 watt hours of power. We chose these batteries because they are the same of many other boards, in particular the LoRa board, so just to say compatible. On average, this means that we must consume no more than 35 to 50 milliwatts, depending on if we want to target 20 or 30 days. These are some measurements that we took. The main section is with everything enabled on the board. This is clearly a lot of power, almost half a watt. And by disabling a series of elements on the board, we could get down to 215 milliwatts. In particular, the Wi-Fi module was the biggest contributor, and we can just turn it off at startup. This is the result that we obtained. So the Wi-Fi module is the main contributor, as you can see. Then we have the QSPI as well, which we can disable, so those are out of the way. Then we have the MCU and Bluetooth modules, which are the main contributors that we need in the project. And finally, the LDO, the linear regulators on the board. These are used to convert from 5 to 3.3 volts and consume quite a bit of power. As I said, 75 milliwatts can go to the regulators, and this can be avoided with a better one, so we decided to ignore this contribution. Nonetheless, there are about 140 milliwatts, which are way too much. We had a limited time, so we did not explore this fully. We did play with duty cycle. So with our target, we should be able to get down with a 25% duty cycle, but when testing, we didn't save as much. The problem is probably with how the CPU is shutting down and how the Bluetooth is shutting down, but we did not have enough time to complete this analysis. These are the measurements. You can clearly see the peaks. This is just the MCU power draw. You can see where it goes from 50 to 30 milliwatts because we are shutting down. And finally, let's talk about some final remarks. So, concluding our project, there is clearly a pretty wide section of future work. This is because the project is very wide. It's wider than we expected at first, and so we had to only implement the hardest parts, or we didn't complete all the details. In particular, we need proper data visualization and data analysis, and we need some better power consumption optimizations on the beacon itself, as I said before. Additionally, the Bluetooth driver that we converted from Arduino and then extended only supports 2 of the BLE roles, so only the connectionless roles. To make this into a proper library, we would need to add the peripheral and central roles, but since this was not required for our project, we didn't spend the time on it. We only implemented a broadcaster, which was already implemented, and we just had to port it, and the observer, which we added. As I said, we spent a lot of time on the hardware. This is because a lot of the hardware we had was not supported or supported only partially, so we had to spend time writing device drivers, debugging hardware problems, and also like analyzing datasheets, implementations, and software that we found online. We did manage to get everything working. We will see this in the demo, but it unfortunately took time away from a more complete, thorough evaluation, and also from the user interface, which is missing. We still believe that the results are quite reasonable and, shall I say, promising. But of course more time would be required for a proper complete system. And finally, these are the blog posts that we made. We chose to talk about some specific parts. So the first post is about the Bluetooth, like everything we had to do to get Bluetooth working. There were a few fixes that we did after the post was made, but all the main ideas are there, and it's quite a long post with all the details. And finally, there is a post on upgrading the firmware on the LoRaWAN Shield that we meant to use at the first. In the end, we didn't use it because we fixed it too late in the process. So we already had our firmware working for the LoRaWAN Discovery board and not for the Shield. But it's an interesting read nonetheless, and now both the shields that we were provided are fully functional.